hawks' sense of hearing is excellent, and their eyesight the best in the entire animal world. Not only can they see greater distances than humans, but their visual acuity is 8 times that of ours. Yet we need to look even further, higher, deeper into the sky.
We live in the lowest layer of the atmosphere, which is the troposphere. The stratosphere is the next layer above us, so it's basically above altitudes of somewhere between 30 and 50,000 feet.
There are processes that take place in the stratosphere that have very direct impact on us.
So it's extremely important to understand the detailed process of water turning into clouds, those particles in clouds settling out. How does that detailed process occur, and then how will it change in the future?
What's been our big problem is getting the airplanes to the right place where they can make the measurements for long enough periods of time to do the observations.
So it turns out the Global Hawk is a perfect tool for sampling this part of the atmosphere. It's a high-altitude aircraft. It flies considerably higher than normal commercial aircraft, but it's also got this extremely long range.
So our bird here can climb to a cruise altitude of 65,000 feet and fly for up to 30 hours.
So we can basically, for example, we could fly from here to Australia in one flight.
So the basic geometry of the airplane, it has a wingspan of 116 feet, which is equivalent to the wingspan of a Boeing 737 transport aircraft, a length of about 65 feet, weighs about 27,000 pounds, fully fueled at takeoff.
In comparison, in the past, people have used manned high-altitude aircraft like the ER-2 or the WB-57. However, those have very short range.
Now that we have the Global Hawks, they have a much longer flight duration. They can get to these key areas to appropriately attack the science questions that we've been thinking about for a very long time now.
Basically, for this program, we searched out the best instrumentation, the best expertise in making these measurements, and invited them to be part of the program for the proposal for the ATREX mission.
Once the major science campaign, the project mission scientist selects the instrument teams, that's really when our work gets started. We will then visit them and begin coordinating all the mechanical and electrical interfaces we need to do to get them mounted on the airplane.
You have to determine everything from the size of the instrument, so you know how much space it's going to occupy or needs to occupy in the aircraft, how much the instrument weighs, so you can be sure that what you design mechanically for installing the instrument on the aircraft is of sufficient strength to be able to hold the instrument in the aircraft.
In some cases you'll see probes sticking out of the airplane, so all that has to go through aerodynamic analysis, etc. Structural mounts inside have to be properly stress analyzed, so we make sure all that happens. So we coordinate with all the proper technical fields to get ready for the instrument to arrive here.
From the time we first start communicating with the instruments teams until we're ready to actually start performing science with all the instruments on the aircraft, it takes about a year and a half of really hard work, close coordination, and a lot of good communication between everybody.
we're using state-of-the-art instruments, or cutting-edge instruments, to measure things like water vapor, clouds, and temperature, and a whole bunch of trace gases.
We have a very sophisticated instrument called the Cloud Physics LiDAR. It's a laser, shoots out the bottom of the nose of the plane, and as the laser goes down, some of the light gets scattered back, and there's a telescope that collects that light. And because you know how long it takes the light to go down and then come back up, you can tell what kind of cloud structure there is below the plane. So if we see very thin clouds, this laser can detect those very thin clouds. We have a meteorological system on board the plane that measures winds, temperatures, and pressure. And it's the best meteorological instrument in the world for measuring these. Imagine how hard it is to measure from a plane that is going a few hundred miles per hour. So it's a really hard measurement to make, and they do it. We have water vapor measurements, 2 water vapor measurements on board the plane. Water vapor is important to look at how air that's going into the stratosphere gets freeze-dried, so you have to have a really high-quality water vapor measurement, and we have 2 instruments to do that. We measure ozone on board this plane. Ozone, as I mentioned, the ozone layer screens ultraviolet radiation, so we have to know what the ozone looks like. There's actually very little ozone in the lower atmosphere, and there's a lot as you get into the stratosphere. So we use ozone actually to tell us the difference between stratospheric air and tropospheric air. We have another instrument that actually sucks little gas samples, has little cans, so it'll suck in a little air, and then you bring those cans back, take them to a lab, and you could literally measure 100 different gases from these little gas sample cans. And that's really important because you can look at all sorts of natural and human-produced gases to look at things like ozone depletion and climate change.
So all of these will tell us how air is transported through the tropical tropopause region and how it's dried to the very dry conditions of the stratosphere.
ATREX is sort of a pathfinder in terms of investigating some of these processes, and when I say pathfinder, it's utilizing a brand new tool, and that is the Global Hawk.
This is a hybrid. It's like a satellite that you control from a control room, like a mission control, but it has nobody in it, like a satellite. So it's really a new and revolutionary way of doing science.
With the science that we do at NASA, we need to combine the satellite data with aircraft data, with modeling data, and even some measurements from the ground all together to answer the science questions the right way.
In 50 years, we'll look back on this plane, and it'll be very common, it'll be used all over the world. I really believe that planes like the Global Hawk are going to change atmospheric science in a very profound way, and for the betterment of everybody who lives here on the Earth.
Everything is ready. We should be airborne soon.